All right, let's go ahead and get started. Couple of housekeeping notes that homework number 3 is due today by the end of the day, so by midnight. If you have any questions, please reach out. I'm around all day, but in and out of meetings. Um, you should have received your midterm back. I put it in the grade book as well. We're going to go over some of the commonly missed questions in the first few minutes of lecture today. And then shoot, I thought I had one more thing to say, but oh well, we'll jump right in here. So overall, I was pretty happy with how everyone did on the final, or the final, excuse me, the midterm. But I wanted to clarify a few things as we go through to make sure that we're all on the same page, because some of these questions you will see again on the final. So this is the first question that you will see on the final. This is one of the things that I think is fundamental to understanding before you get out of this class. And most of the time when I took off points here, it's because people were describing an experiment, but might not have described accurately this randomized part, or may have ignored it altogether and might have just said that the investigator assigned levels of the independent variable. That's great. That's part of being an experiment, but to be a randomized experiment, they have to assign those levels by chance, right? And so we want to make sure we get that in there. And also I took off points if you just, instead of saying randomly assigned levels of independent variable of predictor, this is correct. If you said subjects were randomly selected, that what you're talking about there is scope of inference. So that is wrong for this question. Is right, because you can still have a randomized experiment even if your subjects weren't randomly selected. But you can't have a randomized experiment if levels of the predictor were not assigned randomly. Everyone got this one right? So this means we do not have to put that one on the final. Whoop, whoop. P-value definition, that one will appear again on the final. A couple of things, people kind of did their own thing and kind of a general interpretation. Remember, I gave you in the exam review a Mad Libs description of a p-value. There are some specific text that I want you to use when describing a p-value, when we're being really precise about what that is a probability of. The other common point or half a point that I took off, if you said the probability of seeing a result like this, if the null hypothesis was true, remember, that's just a point estimate. What we want to say is to see a result like this or something bigger or more dramatic, a bigger effect size than what we saw. So that got a few points deducted, or half a point deducted for that. Question number 4 will also be on the final. When can we generalize results from a sample to a population? You have to talk about random sampling here, right? So being able to distinguish random assigning levels versus randomly selecting subjects between these two. So these are 4 fundamental questions that I want to make sure that you know and you understand and you can answer in the most accurate way before leaving this class. So that is why those 4, not 2 because everyone got it right, but 3 out of the 4 because some people missed some points there will also go on the final. So you're ready when it comes. Everyone did really well on the false positive, false negative. No problems there. When we're talking about number 7 here, when we conduct a randomized experiment where 10 students, so our scope of inference, remember our scope of inference is the population that our sample was randomly drawn from. So if you put the number 10 anywhere in your answer, you got points marked off because that's your sample size. That's not your population size. That's not the only population that you can make assumptions out of, right? Some things that were essential here was first year grad students, Department of Pharmaceutical Sciences, University of College Anschutz Medical Campus, and then this enrolled in 2023. A couple of people missed the date. So really thinking about, and the exercise here is that we're trying to really think about how generalizable the results are from our experiment. So better understanding that population that our samples were drawn from. And I know it seems a little bit nitpicky to say 2023, but things change from year to year. Results from 20 years ago are not going to be generalized to results today a lot of times when we're talking about any kind of medical research, right? The three major reasons for one-way ANOVA, if you just said stuff generically like mistakes, I took some points off for there. I was pretty generous overall. If you confused type 1 and type 2 errors, I put that in there. What are the three main visual characteristics of a normal distribution? We went out, this was in our lecture notes, so it had to be unimodal, it had to be symmetric, and there had to be no sharp drop-offs. It looks like a few people searched it up on the internet and came up with a whole other definition. That wasn't the definition we were using in this class. One statistical measure of central tendency and one statistical measure of variability. So let's take a moment here. Statistical measure of variability. This is where the difference between a standard deviation and a standard error of the mean is important. So a standard deviation is a statistical measure of variability. A standard error is a statistical measure of accuracy. Remember, variability is a population characteristic. It's how much do values vary from one to another, whereas standard error of the mean is all about the mean that we're measuring and how good of a job are we doing at estimating that population mean from our sample mean. I appreciate all the feedback I got here in number 12. Everybody got 2 points regardless of what you wrote. To learn that some of the common themes that came up were confidence intervals and skewness and kurtosis. All right, so this was section 2 was our paired t-test. We did fairly well throughout all of these questions. Just a reminder, I'm asking for population parameters. When I'm talking about a paired t-test, that's the mean of the differences. Or if I'm talking about a 2-sample t-test, it's the mean of the groups, the difference of those means. So these are the mu's that we have talked about so far. So making sure that our statistical hypotheses are always about the population. They're not about the sample that we're actually measuring, right? They're all about the population. When we create graphics of a paired t-test or any kind of graphics, just making sure you do once over on that graphic, make sure you got units on all your axes, and then making sure that if you've added anything to the graphic, lines, stars, brackets, anything like that, you need to explain it in the figure legend. Um, for reporting the results section, remember when we're reporting means and we're comparing means, that's when we're interested in the standard error and not the standard deviation. So the expectation in the results section for this problem would be that you were reporting a mean and then you were either reporting the standard error or the confidence interval for that mean, or that a standard deviation is not appropriate here because what we're making conclusions about here is the mean. So we want to know how accurately we've measured the mean. This last question threw people for a little bit of a loop. Remember when we went through our assumptions of a paired t-test, one of the things that we said is that their differences have to be normally distributed. Right? Whatever measure that we're calculating the mean of, that's what needs to fall under that normality assumption. So here, since we were reporting the mean of the differences, it was the differences that needed to be normally distributed. And just like in the homework, when I asked for two pieces of evidence, what I'm looking for is either that you've plotted it, that you've ran skewness and kurtosis, that you've done that the 95 or within one standard deviation or two standard deviations. We went through a lot of different tools, a lot of ways to provide evidence that something is normal. That brings me to the last one. So this was our one-way ANOVA. And this tended to be the section that I took off the most points for in general for everyone. Get my notes here to make sure I'm not missing anything. For null and alternative hypothesis, as long the alternative hypothesis here is a lot of people showed me all the pairwise comparisons, which is great, which is fine, which is completely accurate for the alternative hypothesis that at least one of them is different. Right? For the graphic, I saw a lot of people add tests. So they're adding the brackets and stars or p-values. If you do that, you need to describe what test you did and what the stars or the p-value, where the stars or p-values came from. Right. Also on this one, what I noticed is by default, when you go to make your bar charts in GraphPad, by default, it's going to do your mean and your standard deviation. Right? What we really want is the standard error of the mean or the confidence interval. So if I could tell when your error bars were too big for a standard error. So if you wrote in there that it was a standard error, but I could tell from the error bars that it was not a standard error, then I did take off some points. And then I wanted to point out here on our midterm, oops, to example 2, the last part that I took off for. Again, I've given you a formula here for a results section on a one-way ANOVA. So we start with a sentence about that overall ANOVA with that omnibus test. We have to state that that's significant before we start stating everything else. Because if that's not significant, we end there. We wouldn't do pairwise comparisons if that overall omnibus test is not significant. And so when I ask for all pairwise comparisons between groups and to talk about that, again, what I'm looking for is a difference, a confidence interval of that difference, and an adjusted p-value. The other thing that I saw often done is people copied and pasted and they didn't change the units. So percent here is just because this example, that was the units we were using, was percentage points. Whereas in the test, the units were micrograms of dextrin per gram of tissue. So you needed to change that percentage unit here and here, for example, into micrograms per gram. False negative, false positive. We all did well on that one. Oh, and remember, sorry, keep going on these results section. So we reported the omnibus test, and then as we started going through and stating these differences, making sure that you're giving a sense of direction. So you're not just saying there's a difference between these groups, you're saying that there's more cumulative transport using this one than there is that one. There's more, in the case of the test, accumulation in this group than there is in that group. So making sure you get that direction each time you're talking about a difference in a results section. The last question of the test is, based on these results, would you recommend pretreatment and with lipoplexies, and why? Everybody got full points there if you provided an answer. I wasn't looking for necessarily a yes or no. I was just looking for how you rationalized your answer there. All right. Any questions about what we've talked about on exam one? I do not post solutions for exams, only for homework.
I have a question.
Yes,
So for the 95% confidence interval, we use the units from the problem and not a percentage, correct?
correct.
Okay.
Correct. Because remember, your chart, it should be the same, that your confidence interval should be the same units as your mean or as your difference, right? You're just showing where that range of values is that's possible. But good question. Any others before we jump in? All right. So far in the, the ANCOVA lecture is up. It's a shorter lecture. It's not a full 50 minutes. I think it's closer to 30 minutes along with all of the slides. Um, I did just take the lecture from last year and bring it, so it didn't change in content. Um, that was kind of our last test for dealing with continuous outcomes. So what we're going to do now is we're starting to move into the chapters. We're starting moving into the statistical tests that have non-continuous outcomes. And so what we're going to tackle first here is proportions in their confidence intervals, right? So sometimes we don't have that continuous outcome. Instead, our outcome is actually nominal or categorical. So one of the good examples that we see very often is success or failure of a drug, alive or dead, those kind of nominal outcomes. And so we often, when we have a yes/no outcome, we summarize our results instead of calling it a mean. What we do is summarize it into a proportion or a percentage. So when I use the word proportion, it's a value less than 1. So proportion should range, it's a fraction, should range from 0 to 1, where 1 would be everything. Whereas percentages can run from 0 to over 100%, right? Or not here, 100%, excuse me. And so instead of 0 to 1, it's 0 to 100%. I just want to distinguish those two a little bit. Usually it's not a big deal. Usually you can look at things and decipher whether they used proportions or percentages to describe their results. But sometimes it gets in that gray fuzzy area and you're like, oh, is that 0.2% or is that 20% that they're talking about? So I just wanted to distinguish the words that I use when I'm presenting it as a fraction versus presenting it as a percent. When there's only two categories, we usually refer to one proportion as a P and the other as a Q. Again, no rhyme or reason. That's very traditional. So you might see it when we're doing things like our online sample size calculations and things like that. I want to make you aware. When it comes to how precisely can we estimate a proportion, so sample estimates of that population proportion is going to depend on our sample size. So just like everything else, the bigger the sample size, the more accurately we can measure the more accurately we can estimate the population proportion from our sample estimate, right? And the other thing that's a little different here, the other thing that contributes here is the presence of rare categories. So if you have 1,000 people and only 1 or 2 get the disease, we can't accurately estimate that proportion very well because that's a rare category. And so what I mean, so here we're looking at adverse drug events. And so when we have 5% to 6% adverse drug effects, we can do a better job of measuring the accuracy or getting close to the real measure. When we're at percentages that are like 0.6, 0.4, we do a really bad job of estimating those numbers. So going back to our usual figure, so the width of our confidence interval goes down or has a negative association with sample size, meaning that the higher our sample size, the more accurate our estimate is because the width of our interval is going down. If there is a rare category, then the width of our interval goes up. So this is a positive association here. In GraphPad, there's a new table that we can use that's called parts of a whole. And so it's really easy to input data. Here's just a fake data set of successes and failures. We have 42 successes and 8 failures. So all we're doing is putting the number of each from our population. So we surveyed 50 people. 42 successfully passed their exam, 8 failed it, for example. If we do our analyze button from a parts of a whole, we have a couple of options here, and we're going to do fraction of total. And we're going to ask it to use column totals here because I have my numbers aligned in the column. We can display it either as fractions or percentages. It doesn't really matter. It's just multiplying by 10 here, or 100, excuse me. So we're going to stick with fractions. And then we're going to ask it to calculate a 95% confidence interval. And so here I'm showing down in the method that I've changed the recommended default to the Klopper-Pearson. And the reason why I did it here for this specific example is that this is the method that the book used. And so to get our answers to match what the book says, this is the option that you would have to use. Would I actually use this in practice? Probably not. I would go with the recommended version, but I wanted to make sure if you were doing things on your own that you could recreate results we saw. And so all that this does is calculate that proportion of successes, proportion of failures, and then assigns a confidence interval to those. And so you can see that it did, that the results that I report down here in the table are terms of success, right? And so I'm going strictly with what's here for what I reported below, but I could have easily done what's the proportion of failures in my data set and taken the second row. Nominal data are not very efficient. So what do I mean by efficient here? It means I have to have really large sample sizes to be able to get a confidence interval that isn't gigantic. So for example, if I'm measuring a binary outcome, I've got a percentage of successes. I only have 10 samples. My confidence interval is huge, right? It goes from 20% to 80%. So it really takes away from the interpretation of my data set. And I really got to go big to narrow it down even into the 40s and 50s down here. So I think, especially as you move on into your research career and you're designing studies, sometimes it's easy to say, oh, well, let's make a binary outcome so that our outcome is really clear. It's easy to work with, blah, blah, blah. But there is a very serious weakness of making your outcome dichotomous. It's that you have to, when we do that, we require really big sample size to be confident in our estimate of that proportion. It doesn't matter which one we talk about. In general, if we need the confidence interval for a proportion in the opposite category, so we talked about the number detected in the context of the number successful, the point estimate of successful, but we could have as easily done it for failures, right? And so all we did to estimate failure was to do 1 minus 0.84. Easy to convert if we've already estimated everything. Likewise, we can get the confidence interval from subtracting each value from 1. Right. So this equals this equals that. Unlike the confidence intervals we've talked about so far, confidence intervals for proportion are asymmetric, meaning there's one side that's shorter than the other side, right? So my error bars don't come the same distance out of either side. And really that asymmetry is due to the fact that you can't be above 100. You can't be below 0 in this context. You have to stay within those bounds, and so that makes an asymmetrical confidence interval. The only time that it will be symmetrical is when the point estimate, or that proportion that we estimate, is exactly 50%. So in that case, that both ends are within the same distance, both boundaries are within the same distance of our point estimate, and it will be symmetric. So now we've calculated proportions, we've gotten a confidence interval. What if we want to compare that proportion we've estimated from some known value? And so we want to see if our sample data is consistent with a specified proportion. And to do that, we use what we're going to call a goodness of fit test. And I'm trying to be very specific here because we're going to talk about, we use a goodness of fit chi-square test. In the next lecture in chapter 18, we're going to talk about a different kind of chi-square test. So I'm trying to be real specific here. So the example that we're going to have is that a company produced pressurized canisters of drugs for asthma inhalers. They have 2 machines, the Allegro and then Dante. And we know that the Allegro produced 61% of the canisters, and Dante produced 39% of the canisters. So we know these numbers for the entire population. These are not an estimate. We know exactly, right? What we want to do is take the canisters that we get returned as being faulty, so bad canisters, and look to see if both machines are equally as bad at producing faulty canisters. What we would expect to see back is the same proportions that were made with those, right? So what we saw was 126 canisters were returned, 52 from Allegro and 52 from a Dante. So I want to know if the proportion of my Allegro machine derived inhalers that were returned is equivalent to the proportion of canisters from that machine that were produced. All right. So in this case, in the Allegro, we observed 52 canisters and we observed 74 canisters in Andante. So what we're going to do is compare that to what we would expect to see if our 2 machines were equally reliable. And so to get to that, we take the total number of returned canisters which is this 126. So it's just the 126 just comes from the 52 plus 74, right? And then we would multiply that by the proportion of canisters that were produced by the Allegro machine and the proportion of canisters that were produced, so in our entire population, by the Andante machine. So we would have expected to see about 67 of those canisters be from Allegro and about 49 be from Andante if they were equally reliable. So how we calculate a chi-square test is we compare what we observed versus what we would expected under our null hypothesis, that it was equal to some given proportion, right? And so we're just going to subtract those two values for both machines. We're going to square them, get rid of the sign, right? And then we calculate this kind of a proportion. So what it is it's this difference squared divided by the expected, and we call this our chi-squared value. And that's what that's what the tables in the back of any statistics book do, is convert that chi-squared value into a p-value. But luckily, we can get the computer to do it for us. We're going to do that parts of a whole again. This time I've got my Allegro and my Andante number of canisters returned in the same column. I'm going to do, instead of fraction of total, compare observed distribution with expected distribution. And so here I'm going to go to percentages to make my life easy, because that's how the expected percentages were presented in the write-up. And we're going to do a chi-square test for goodness of fit. Again, this is what the book starts out with, so this is what I'm showing you. We will get to binomial tests in a minute, which is recommended over this chi-square test of goodness of fit. I put in my expected values based on the text, remember? These are my expected values right here. And so what that does is give me a p-value. So what this p-value is testing, right, is my null hypothesis is that the p for Allegro is equal to that 60, sorry, let me do that again, is equal to 61%. And our H alternative is that the P for the Allegro is not equal to 61%. So because this is significant here in my two-sided p-value, I'd say that the machines are not equally reliable. And so we can see that for the Andante group, we observe a lot more canisters returned than we would expect if they were equally reliable, and our percentage is bigger. Yeah. However, there is what we call a continuity problem. And so when we take that chi-squared value that we talked about by looking at the difference and dividing by the expected, we're assuming that this chi-squared values are continuous to go from the chi-square value to a p-value, right? But since they're discrete outcomes, that really isn't completely true. And so what we do instead is do what we call a Yates continuity correction. And so that just helps us out a bit when counts are small, to account for that slight bias or that assumption in our data set. And so the Yates continuity correction for the goodness of fit is described really well in the book, but it's not applicable in PRISM. So what is in PRISM is that exact binomial test, which is very, very close to what we're talking about in this Yates continuity correction and actually even better. And so instead of doing a Yates continuity correction, we actually use that binomial test. And so here where we make that change, right? We take the recommended binomial test. We still get a highly significant result. We still see very big differences, but now we also get a 95% confidence interval for our percentages. So in this case, it really doesn't matter which test we use, we come to the same conclusion. We can do a similar goodness of fit test when it's more than just yes, no, Allegro, Adante. If there's 3 levels, we can do the same thing. We're still going to get what we consider an omnibus p-value. P-value. So it is testing that null hypothesis that the P for leaflet A is equal to 33.3% and PB is 33% and PC equal to 33%. So they don't do formal post hoc testing in this situation. You would have to show an omnibus test and then do those tests separately, the pairwise tests separately to get to an answer there. So what did we learn? We're going to treat our nominal outcome data differently than we are our continuous outcome. So you could give everyone a score 0, 1 for that dichotomous outcome and run a t-test looking at means, but it's not going to be as accurate or as appropriate as the chi-square that we're showing here. Any questions?
No, not right now.
Thank you. All right, moving on. So that was when we were comparing a proportion that we estimated to a known proportion, right? A lot of times what we want to do is instead of using that goodness of fit, we want to use what's called a contingency chi-square. So it's determining if there's difference between 2 sets of observed proportions, right? So maybe our outcome is 0, 1, survived or failed. We may be looking at cases and controls. So we're estimating population proportions with our samples for both proportions that we want to compare. So in a contingency table, so our example here is we're looking at a new test design for an IUD, and then we're measuring or observing how many in each the control design and the test design are spontaneously expelled. So this is a negative outcome with an IUD. And so in the control design, we implanted 2,000 IUDs. And in this test design, we implanted 2,000 IUDs. 13.4% in the controlled design were spontaneously expelled, and 11% in the test design were spontaneously expelled. So we either want to compare this 13% to this 11% and say, are those significantly different? Or this 87% to this 89%. You're going to get the same answer statistically with p-values if you think of it conceptually as comparing the proportion expelled as you would comparing the proportions that were not expelled. And so in a contingency chi-square test, we have a nominal scale factor as our predictor and a nominal scale outcome. Right? So our predictor here is the design of the IUD. So this is our predictor. And this is our outcome. Expelled or not expelled. Okay. It doesn't really matter how we orient the tables. For this chi-square test, if we talk about the percent being expelled from each design, or we talk about among those that were expelled, what proportion were from the control design and what proportion from the test design. We're going to get the same p-value from our contingency chi-squared analysis for both tables. It's really about what makes it easier to explain. What is more intuitive to you when describing your results? So for instance, in this one, I feel like it's easier to talk about the proportion that were expelled in each test design. So what influences the significance of this? So the contrast between the two sample proportions. So the bigger the difference between the two sample proportions, the more likely you are to get a significant result. The size of the two samples. And finally, that presence of rare categories still contributes to significance in the contingency chi-squared, just like it did in that goodness of fit chi-squared. So to kind of summarize what that table is saying, a large difference between the proportions in two groups being measured, being compared, what things lead to a significance. So a large difference, a large sample size, and all categories are reasonably well represented. So if it's two levels of categories, it's 50-50. If it's three levels of categories, it's 33, 33, 33, or something similar. Where you're not likely to get a significant results is if you have a really small difference in proportion between the two groups, if you have really small sample sizes, and if one of the categories is super rare within your groups. So if you're trying to compare 5% to 10%, it's going to be harder to come up with a significant result, whereas 55% to 50% would be easier to come up with a significant result. Again, that Yates continuity correction comes back into play. So just like we had to use a correction and we actually switched to a completely different test in the goodness of fit, in the continuity correction, in the contingency chi-square, we also have to do that correction. One caveat to this is that the Yates continuity correction is only available when you have just two categories. When we move out into three categories, you have to accept this little bit of difference and use the traditional chi-square without any kind of correction. So what we're going to do here, so we've moved from parts of a whole table to what we're calling a contingency table. And here we put one outcome across our columns and one variable along our rows. So for this design, I'm showing you the outcome along the columns and the predictor along the rows, but that's simply by choice. And I put not a steadfast rule. We'll talk a little bit on next Monday about when this ordering does make a difference when you're calculating some other variables. We're going to select the chi-squared test from our Analyze Data button. And here they give us three options: a Fisher's exact test, which we'll talk a little bit about in a minute, the Yates continuity corrected chi-square test, and then just a regular chi-square test. There's really no reason we'd use this regular chi-square test unless we had more than two groups. And at that point, the Yates would look like this, right? It would be grayed out. So as always, we got lots and lots of data in these results section. So the top is this first part is all about the p-value, right? So here on our IUD example, we get a significant p-value. So what that's telling us is that the proportion of IUDs expelled was different between our test design and our control design, right? And so here they've just repeated the data that you put in, except for adding these total numbers to it, right? And then here, this is where it doesn't really matter which order you put it in for this particular test, because they can show you percentages as in the percent expelled by control and percent expelled by test, or if they can represent it as a proportion of column totals. So here again, of those that were expelled, there was 55% of those were from the control design and 45.31 were from the test design. So all explaining the same data, whichever way rolls off your tongue a bit better or gets you to your conclusion. Rarely do we use this percentage of grand total. So the example for a method section here, remember, I have to tell exactly the type of test I use. So contingency chi-square test with a Yates correction was used to determine the difference in the proportion of patients whose IUD was expelled between groups of patients that received the control design and the group of patients that received the test design. So I've told you the name of the test. I've told you the outcome, right? And I've told you the predictor, control design and test design. And I've included my version of GraphPad. Remember, these are the key points to include in that method section. The name of the test, what your predictors and outcomes were, and then the name and version of the software that you used. In this case, we could say, for this case, we would say that there was a significantly higher proportion, and this is where we give our chi-squared results, and give the direction of patients whose IUD was expelled and the patients that received the control design, my estimate, compared to the patients that received the test design. Here are my patients. It's not very consistent if people put a confidence interval on these estimates or not. You can if you wanted to, but you don't necessarily have to. We can do larger contingency tables. So here, this is how reminders were sent to patients, and they were comparing whether or not then the patient attended their doctor's appointment or didn't attend it. So now instead of having 2 levels, I have all 4. So, oops. So like we've talked about before, in the goodness of fit test, we'll get that overall omnibus that tells us there's some difference in attendance rates between the 4 reminder modes, but we won't know which one is there. So you might do the overall omnibus test, get that p-value, and then do by hand some post hoc comparisons. But the name of the game, keep it simple, keep it clear. Remember, you've got some multiple testing whenever you go down and start doing all pairwise comparisons. So when thinking about experimental size, remember things that can add to the sample size necessary. The presence of a rare category, if there's a small difference. So if the difference is big, it requires less sample size and vice versa. And then the power that you require. One of the nice things about proportions and binary outcomes, it's really, really easy to do power calculations, right? So what it's going to ask you in a power calculation is the assumed proportion in one group and the target proportion in the other group, right? So we can no longer say in our power and sample size calculation that we want this difference, 4 percentage points difference between our 2 proportions. That's not going to work. The calculations need to know how rare or how common the event is. So the Fisher's exact test. So even when using our Yates correction for contingency chi-squared, there's some approximations that work satisfactory when there's large counts involved, but we start to get a bit biased when we just have small counts. So in general, low counts are not a problem, only low expected counts. So remember when we created that table of expected observations versus observed, it's those expected observations that matter. So our alternative when we have those small sample sizes or low expected frequencies is the Fisher's exact test. So there's a lot of advantages to using the Fisher's exact test. The reason why we have two and some of those approximations, again, goes back to back in the day when people were calculating things by hand or didn't quite have the computational power to do it. A Fisher's exact test is what we consider to be computationally expensive because it looks at a lot of permutations or iterations of the data set. So when people were doing statistics by hand, they were doing everything they could to avoid the Fisher's exact test. Now that we have computers, it's kind of our default, right? There's really no consensus on what the low stands for and what in low expected frequencies, right? So a lot of statistical packages will give you a warning. We'll give you some kind of note that lets you know when there's an expected count of less than 5 in any cell or any two cells. Therefore, if there's really any doubt because there's no steadfast rule, you just go ahead and use a Fisher's exact test. So I will never count off points if you use a Fisher's exact test, but you didn't need to. But I would count off points if you use a contingency chi-squared when you needed to use a Fisher's. So I'm going to pause right there. We are going to pick up from here, finish this last bit out on Monday. I'll go ahead and stop the recording.